In this video, we look at the difference between continuous versus discrete probability distributions. So we've looked at discrete distributions before. Basically, just a reminder that discrete distributions can be obtained by counting. So we count the different results. There are only a finite number of possibilities. And the probabilities are the areas of the bin. So in this example over on the right side of the page here, over here, we can see this is the probability of flipping a coin and getting heads. So this is the probability of 0 heads, 1 head, 2 heads, and 3 heads. And so we can look at the probabilities here. So the probability of getting 1 head is really just the area of this bin, this little rectangle here. It has a width of 1 and a height of 0.375. And we can get that by looking at the tree diagram for tossing 3 coins and seeing how many times we get 1 head and so on. So the area here is just 1, the area of that bin is just equal to 1 times 0.375. And we can find, what's the probability of getting a 1 or a 2? That would just be the area of this rectangle right here. So it has a width of 2 and a height of 0.375, or we could just kind of double the result that we have already. So that's how we can find for the probabilities for discrete distributions, and we've kind of looked at that before. We're going to start looking now at continuous probability distributions. Now, just a reminder that for continuous data are obtained by measuring. So you can measure somebody's height, for example, and you can have somebody that is 184 centimeters, or they can be 184.275 centimeters. Basically, between any two values, there are an infinite number of points in between, so long as you can measure precisely enough. Typically, for a continuous distribution, instead of breaking the independent variables into discrete units, we break them into intervals because it is a continuous value. And we'll see that shortly here as we look at this probability density graph. So what a probability density graph is, it's a histogram that basically shows the probabilities of different values. So not that different from kind of what we've looked at up here. The only difference is that now we're looking at a continuous probability density graph. One of the things that you should notice here is that along the independent axis, the x-axis, we're not showing individual values, we're showing an interval. So this first interval would be, this is a graph, by the way, of age distributions of teachers in Ontario high schools. So this first interval would be the interval of teachers that are aged 25 to 30 years old. So we can see that there, and that's one of the important differences between a discrete distribution and a continuous distribution when we go to graph it, is that we're looking at intervals. And again, we can still find the area. The area of teachers who are age 25 to 30 would be the probability of getting a teacher that's between the ages of 25 and 30. We're looking at the area here. Now the trouble with this occurs a little bit, up in the discrete distribution example. We looked at the width of this section right here and said, well, this had a width of 1 and a height of 0.375. The trouble here is that we have a width of 5 years here. So if we take that 5 years and we multiply it by the height, so the height in this case is actually 0.1428. And that says that in the caption below the graph, so you can get an idea here. So if we take that 5 times 0.1428, we'll get a value that is not quite accurate. And the reason for that, I'll show you why, maybe we'll do that right now, is that let's find the area. I'll just change my pen color here so we get a good sense of what's going on. Let's find the area of this whole rectangle, so that all possible outcomes. Now we know if these are all of the teachers in Ontario, and the probability of looking at a teacher between the age of 25 and 60, if there aren't any other teachers, should be 1. But how do we find the area of this polygon? Well, the area of this rectangle should be the length, which is here from 25 all the way to 60. So 60 minus 25, that gives us a length of 35. And then we multiply that by the height of this rectangle, which is from 0 all the way to 0.1428. And if we work that out, we get a result of 5. Well, if the area of this entire rectangle is supposed to represent the probabilities, then we can't have an area or a probability that's equal to 5. So it turns out that this area should equal 1. So the area we really want to equal 1 to represent the probabilities. Remember that if it's the probabilities of everything, all of the possible probabilities should add up to 1, and we're getting an area here of 5. So what we really need to do is not this right here. We need to actually divide our bins not into 5-year chunks, but if we say that each bin is 1 unit wide, then we'll get an area of 1, because we'll have I guess there are probably 7 different bins here. Multiply that by the height and go from there. I'll show you what I mean here. I have another graph here. So here's the first graph that we started with. Notice the ages along the bottom here in intervals from 25 to 30, 30 to 35, and so on. Well, now if we just sort of scale those values and just call this, our first bin and our second bin and so on, now we have a distance of 1 here and a height of 0.1428. And that would give us the probability, say, that somebody is a certain age. So for example, if we want to know the probability, what is the probability that somebody's age is greater than 55? So that's this column, this bar in our graph. Well, that's really just the same as saying that the probability that the person's age, I'm going to use X here because it's kind of scaled down to this graph here, is, we said greater than 55. What's the probability that X is greater than, whoops, I wrote a 6 there, that should be a 7. Let's see if we can fix that. Probability that X is greater than 6. Well, that should just be the width of the bin here, which is just equal to 1, times the height of the bin to find the area of that section, which was 0.1428. And again, we can use this information to find probabilities for other values. So for example, we could find what's the probability that somebody is over the age of 40. Well, here's 40 in the graph, so over the age of 40 would be kind of from here on over. So this part of the rectangle here, this rectangle here. So that's how we can use probability. That's actually a little bit about the difference between discrete and continuous probabilities. This unit explores continuous probabilities. I did want to make the connection between continuous and discrete probabilities. And one other thing that I will mention that will be handy is something called a frequency polygon. So we've looked a lot at histograms, and we're going to start moving away from a histogram into what's called a normal curve. And to do that, we first look at a frequency polygon. So the frequency, this is a histogram. It shows the frequencies for different values. The frequency polygon basically draws what's called a polygon. It's an enclosed figure by connecting the midpoints of the bars in the histogram. So you can see that in here that we have, let's see if I can, right here, oh, hang on a second, let me grab a pen. So we have the midpoints here, here, and all the way through, and we just connect those values. And what that does is it creates this polygon for us, which is why it's called a frequency polygon. And I've just, in the picture below, I've just stripped out the histogram so you see just the polygon. So again, it's an enclosed figure. We say it's enclosed because it also contains the x-axis. And again, what we're trying to do is we're trying to find the area under a curve. Now that's a very complicated process. We're going to look at some ways to make that easy, but I did want to highlight the frequency polygon just so you get an idea of what that's all about.